Okay, in this video I'm going to continue on with exercise 6b of the book Fundamental Applied Mathematics. We're on page number 162 and the question is 8. It reads: a bobsleigh slides down a frictional surface which is inclined at an angle 30 degrees to the horizontal. It starts from rest and travels a distance of 20 meters. Why may the principle of conservation of energy be used here? Find its final speed. So first of all, we realize that this bobsleigh is only operating in a gravitational field, and the principle of conservation of energy holds in gravitational fields. Next, I've drawn a sketch of the motion, and I know it looks quite busy, but at this stage we don't really need to do most of this. The only thing I've done is I've resolved the position vector, or the displacement vector. So it starts up here and finishes down here. We're told that this distance from here to here is 20 meters, so it's going to be 20 over 2 in the j-hat direction and 20 root 3 over 2 in the i-hat direction. Notice the displacement is actually, if we're talking about vectors, it's negative I, negative j sort of thing. Alright? We've put in the weight vector in green here and the normal vector in red, but you'll find that they're irrelevant. So the first thing I'm going to do is define point 1 as being where it starts and point 2 where it ends. And at this stage you should be aware that you can define your 0 point of your gravitational field to be anywhere. So this time, just to be awkward, I've defined it as being at point 1. Now what you need to realize that is that as a result of it, this direction is positive and this direction is negative for gravitational energy, which means this gravitational energy here is negative. Next, because we're talking about a gravitational field, the only displacement which matters is its vertical displacement in the j-hat direction. So it's the only height that matters is 20 over 2 or 10 meters. So let's apply the principle of conservation of energy. The kinetic energy at 1 plus the potential energy at 1 is equal to the kinetic energy at 2 plus the potential at 2. So what do we have as a result of that? The kinetic energy at 1 is half m times, well, it slides down the frictional surface, so we're going to say this is equal to 0 squared, plus the potential energy, which is mg times, well, I told you I've defined here as the 0 point, so that's going to be 0. Then we're going to have the kinetic energy here is half m, and in this case we're going to go at this point down here. I'm going to say it's got its maximum kinetic energy at v squared. Then the potential energy. Now, first of all, we know that the potential energy is a negative number, so we can straight away write a negative number in here. Then mg times the displacement, which is 20 over 2. Now, be careful. If you wanted, you could have plus mg, but use the negative 20 over 2. Okay, but make sure it's negative because it's a negative gravitational energy. So this is 0, so is this, and if we move this component over, we're going to get that 10 mg is equal to mv squared over 2. So we're going to get the 20 mg, or 20g, rooted, is equal to v, which is something we've seen plenty of times at this stage. So it has to find its final speed, so let's go ahead and do that. 20 multiplied by 9.81, root of the answer, 14. So bear with me one moment and I check that answer. So we're on 6b, question 8. And that's correct. So thanks for watching. Please pass it on to your friends and subscribe to my channel.